Okay, first question. So we're trying to work out the speed of the body after 40 seconds, sorry, assuming no other forces are acting, and we've been given this force time graph, and as soon as we're seeing this, we're hopefully thinking that the area under a force time graph is equal to the change in momentum. Seeing as we know the mass of the object, we know the change in momentum, we can calculate its speed, which is what the question is asking, so we should be fine for this question. The area under this graph is the area under a triangle, so it's going to be a base of 40, it's going to be a height of 10, and so that is going to leave us with an area of 40 times 10 divided by 2 because it's a triangle, so that is going to give us a change of momentum of 200 kilogram meters per second. So that's equal to change in momentum. Now we know that the change in momentum is equal to the mass times the change in velocity, and we're trying to work out what the change in velocity is going to be. So change in velocity, by rearranging the equation, is going to be change in momentum divided by the mass. The mass is given to us as 0.25 kilograms. So this is going to be giving us 200 divided by 0.25, which of course is going to be 800. And that's going to be meters per second. Now this, of course, is the change in velocity, but we are told that the object is initially at rest. So if its speed is initially 0, then its final speed must be 800 meters per second, and that must mean that the answer for the first question is C, 1C. Now our second question is a classic example of a conservation of momentum type question. We have a parent nucleus first of all with a mass of capital M, and it's stationary, so its momentum initially is going to be 0. After that we have a daughter nucleus being produced and an alpha particle. The alpha particle has mass little m, so the daughter nucleus is going to have mass big M minus little m. It's the difference between the parent nucleus and the mass of the alpha particle. The total momentum of this system has got to be equal to 0 because the initial momentum was 0 and momentum is conserved in this interaction. So the thing that we're trying to work out is the speed of recoil of the daughter nucleus. The problem that we have is that we're not actually told what the velocity of the alpha particle is, but we are told that it comes out with a kinetic energy capital E. So we're going to use the equation for kinetic energy to bring these things together. So let's set up the problem and see if we can solve it. First of all, our mass m with a velocity equals 0, and then afterwards, and of course this means that the momentum is going to be 0 as well. Afterwards we have a daughter nucleus. The mass we said was m minus little m. The alpha particle has mass little m. Let's call this one V, or V alpha I suppose we could call it, doesn't really matter. And this is the one we're trying to work out, the speed of recoil, which is u. And we know one final thing, we know that the kinetic energy of the alpha particle Ek is going to be given as E in this question. So we need to find out what u is going to be. So the first thing we know is that the total momentum of these objects is going to be 0, as we said. So if it's going to be 0, then the size of this one is going to have to be equal to the size of this one, otherwise they won't have one subtracting from the other to give us 0. So the momentum of this one, of course, is going to be m minus little m, which is the mass of the object, times the velocity, which is u. And that's going to have to be equal to minus the momentum of this object, which is going to have to be the mass times, again, the velocity, which we can call v alpha. Okay. Now what we're going to do is rearrange this equation. We're going to find that u is going to be equal to m v alpha divided by big M minus little m. Now this gets us most of the way there, but we've still got a problem because all of our answers are not in terms of the velocity of the alpha particle at all, they're in terms of the energy. We have these E terms. So we're going to need to come up with an equation to substitute this V alpha for something in E. So we're going to need to remind ourselves over here of the equation for kinetic energy. Kinetic energy is going to be EK is a half mv squared. Oops, half mv squared. And that's of course the velocity of the alpha particle. So the velocity of the alpha particle, by rearranging, we can times both sides by 2, divide both sides by the mass, and finally square roots. And all those things together, with a bit of algebraic manipulation, give us a velocity of the alpha particle of the square root of 2e over little m. So now we can substitute this term into this, and we can end up with the correct answer, hopefully. So we'll continue this bit over here. So we have recoil velocity u is going to be mv alpha over m minus little m, and it doesn't actually matter. You might have noticed that really we should have put a minus sign in this one, but seeing as the question is asking us for the speed rather than the velocity, the minus sign is really not all that important, but we'll put it in anyway for completeness. So this would be the same as saying it would be m v alpha over little m minus big M. There we go. So now we're just going to substitute this v alpha in. So we're going to have m square root of 2e over little m, all divided by this term here, which is little m minus big M. There we go. Now, I have this surd that I want to manipulate. I want to get this m somehow into this square root. The only way of doing that is by squaring it, is to recognise that this is essentially the same as saying that this is the square root of m squared, isn't it? And if we multiply two surds together, we can just amalgamate the whole thing into one. So this is going to be the square root of 2e m squared over m, all divided by m minus big M. Now, we need a third piece of paper to finish this one off. Okay. I'll move this over here for the time being. Okay. So we're noticing we've got an m squared over m here, so that's just going to cancel, isn't it, to the square root. So we have u is equal to the square root of 2e m over m minus capital M. There we go. And we can rearrange this again. The question, as you'll remember, has got it in terms of this. So I'm looking at my answers and I'm noticing I've got a square root of 2 times e times m. That's the same as this one here. So that looks like it's in a good spot. The only difference, of course, is that this is 2 me over big M minus little m. But I'm remembering again that this is the speed of recoil of the daughter nucleus. And so I don't need to worry about the sign at all. I could literally say that the speed of recoil, which is the size of u, this is a symbol, these two lines meaning the size of u, not worrying about the direction at all, that can be written as 2me, just changing those two around, over capital M minus little m. And that, of course, is the same as A. So the answer to question 2 is A.